Okay, so y'all take your test on limits? How'd that go? Yeah?
I'm going to get it back tomorrow.
Nice.
I got everything graded, but the pre-response, I don't know. Well, overall, and I don't know if this was his, but overall, some of the questions I was finding wrong. And I was thinking to myself, I'm not disappointed. I'm disappointed in myself. Like, clearly there was something that I didn't do right for you to miss specific questions. So we'll look at it. Don't worry. It'll be fine.
Okay, so guys, limits is the foundation for everything that comes next. Okay, so limits aren't going away. Okay? All right, so we're moving into what we call derivatives. So differential calculus, and then next semester we'll look at integral calculus. So we're going to learn today how the derivative is tied to a limit, and then you'll understand later next semester how an integral is tied back to a limit. All right, so rates of change, something you're already familiar with, yes? Rate of change, what's another word for that? Slope, okay? So rates of change, okay, plays a role whenever we study relationship between two changing quantities. All right, so an example that we're all familiar with, velocity, okay, speed. Okay, velocity is change in position with respect to time. So if I tell you I get in my car and I drive 50 miles per hour, you know that my position is going to change 50 miles each hour, okay? So velocity is just one example of a rate of change. Now, this example, if I go 200 miles in exactly 4 hours, can you tell me my average speed? 50. How'd you do that? Just divide, right? 200 divided by 4. So on average, the speed was 50 miles per hour. Does that mean I was driving on cruise control, going 50 miles per hour the whole interval of time? Not necessarily. It could mean that, but not necessarily. It just means on average, my position changed 50 miles each hour. Okay, so, but at any given moment, we can be going faster or slower. But all you cared about was the distance traveled divided by the time that elapsed, right? Distance traveled divided by time that elapsed. So that's average velocity. All right, so velocity is just one example. You've been calculating slope since Algebra 1, right? Or maybe even 7th or 8th grade, yes? What's the formula for slope? There you go. Y2, right here? Delta y over delta x? Y2 minus y1 over x2 minus x1, yes? You've seen that before? It's just been a while. Okay, so this is what you learn in Algebra 1, right? Y2, sometimes they say rise over run. Do you remember that? Okay, change in the dependent variable divided by change in the independent variable. All right, so that's your Algebra 1 slope. And then maybe in Algebra 2, you did the same thing, but with function notation. Does that look familiar? So f of b minus f of a over b minus a. Is that the same thing? It's just y2 minus y1 over x2 minus x1. And then maybe in pre-cal, you even stepped it up just a little bit more. And you looked at it like this, f of x plus h minus f of x divided by x plus h minus x. Does that look familiar? Some people are saying no. Do you need to pull up your notes? Little dots. All right, so she was showing me this, that y'all did this last year. So a lot of what we're about to do, you guys have already seen at one point. It's okay that you have forgotten, okay? But we just wanted to show you that this is something you might have seen before, right? She remembers. Yeah. Okay, so guys, is this the same thing? Is this just y2 minus y1 delta y over delta x? And then what's x plus h minus x? Just h, right? So delta y over delta x. So that's kind of been like the evolution of slope as you progress through your math courses. Okay, so average rate of change. It's rate of change over an interval, okay? So let's look at this example here. Let me erase this. Oh, okay. All right, so function f of x equals x squared, the quadratic function, something we're all familiar with. It says find the average rate of change over the interval 2 to 5. So what do we need? 2 points, right? So x equals 2, So we've got the point 2 and the corresponding y-coordinate f of 2. We have another point at x equals 5 and the corresponding y-coordinate f of 5. So y2 minus y1 over x2 minus x1. So f of 5 minus f of 2 over 5 minus 2. What's f of 5? When x equals 5, what's the corresponding y-coordinate? 25, right? Because the rule says take the x-coordinate and square it. So f of 5 is 25. What's f of 2? 4. Okay, 2 squared, 4. So I make the substitutions. Over 5 minus 2. So again, y2 minus y1 over x2 minus x1. We end up with 21 divided by 3, so 7. Now guys, so the average rate of change between those 2 points is 7. And guys, graphically, that corresponds to the slope of the line connecting those 2 points. Do you remember what this type of line is called? You're allowed to say no. No? A secant line? A secant line? The line that connects 2 points? So guys, the slope of that secant line corresponds to that average rate of change. So we got to make the connection between slope of a secant and average rate of change. Slope over an interval is average rate of change. Okay? All right. What if we did the same type of problem, but without the graph, just with a table of values? So we've got this differentiable function. Do y'all remember that word tells us that the function's good? Nice. All right. So we've got 6 snapshots of this function, but all we're concerned about is what is the average rate of change over the interval -1 to 5. So same thing. So this is like our A and B. So all I care about is those 2 endpoints of the interval. So f of 5 minus f of -1 over 5 minus -1. So we don't have to work very hard for these values because they're given to us in the table. So what is f of 5? 15. What is f of -1? 3. 5 minus -1? So 6. All right, clean that up. What do we get? 12 divided by 6. So 2. So the average rate of change, okay, on that interval is 2. If I were to look at a graph, the slope connecting those 2 points would be 2. Okay? All right, so this doesn't feel like calculus, right? This is stuff you've already done. All right, but you will be expected to do this as part of bigger things, okay? So you will be expected to do this. Sometimes it is as straightforward as here's a table of values, find average rate of change. So don't forget, average rate of change, slope of the secant, slope between 2 points. Okay? All right. In addition to knowing average rate of change, okay, which is rate of change over an interval, we may also want to know the instantaneous rate of change at a single point. Okay? So we looked at average rate of change, slope between 2 points, slope of a secant line. So if we make that connection, average rate of change is slope of a secant, then we can think of instantaneous rate of change as slope of a single point, which would be slope of a tangent. Okay? Do we understand the difference between secant and tangent? I think she had a good picture over here, right there. So do you see her secant line right here? Slope between 2 points. Versus slope of a tangent line is slope at a single point. Okay? So we're making the connection. Slope of a secant, average rate of change. Slope of a tangent, instantaneous rate of change. Okay. All right, but here's our dilemma. We looked at 3 different formulas for how to find slope. All of them require 2 points. But right now, it says consider this function. f of x equals x squared. A while ago we found the average rate of change over an interval. Our job now is to find the instantaneous rate of change at a single point, at an x-coordinate of 2. So this is our goal. I want to find the slope of this tangent line. All right, but how do we find slope if we only know one point? All three of those formulas we looked at earlier require a second point. So how about we just generate a second point? So I'm going to start here, move over some arbitrary distance h, and create a second point on this curve. So guys, if we start on the x-axis at x equals 2, and we move over h units, where would we be? 2 plus h. So now I've got an x-coordinate 2 plus h, and I can generate this second point. So I have a point 2, comma f of 2. This point 2 plus h, and the corresponding y-coordinate f of 2 plus h. All right, so once we have 2 points, okay, I have a formula for that. y2 minus y1 over x2 minus x1. So f of 2 plus h minus f of 2 divided by 2 plus h minus 2. What's 2 plus h minus 2? H. And doesn't that make sense? Because this formula is just delta y over delta x. And here, that is our delta x, right? That h value is that delta x. So that denominator will clean up to be h. All right, but these values we have to work for. What's f of 2? We did that earlier, right? F of 2, the function rule says take the x-coordinate and square it. 2 squared is 4. All right, but what about f of 2 plus h? F of 2 plus h. So our function rule says f of anything is that anything squared. So what do we want the input to be? I need to find f of 2 plus h. So just like when we wanted to find f of 2, we take the x-coordinate and square it. Same thing here. To find f of 2 plus h, I take the x-coordinate and square it. So we're using 2 plus h as our input. All right, what do we get when we take the quantity 2 plus h and square it? Okay, so plus some other stuff. Okay, so guys, be careful. Like, it's not legal to distribute an exponent. It doesn't work that way. You'll go to jail. Oh yeah, right here, right here. So that doesn't work. Math doesn't work that way. Okay. But it's okay. Like, if you forget, just work out a simple problem. Like, if I did 2 plus 3 squared, what's 2 plus 3? 5. 5 squared? 25. If I were to distribute, that would be 2 squared, which is 4, plus 3 squared, which is 9, 13. Can I borrow $25? Next week I'll pay you back 13, call it even? No? Okay, so it's tempting to do that, but just be careful. Okay, take the time to expand that. All right, so this means we're taking the quantity 2 plus h and multiplying by itself. So we can distribute 4 plus 2h plus another 2h plus 4h plus h squared. Okay, so don't forget that middle term. All right, do I have everything I need to make substitutions? Let's see. All right, so f of 2 plus h. We have to substitute these 3 terms. Okay, so all that goes here. And then f of 2, what do we get for f of 2? 4. And then we already decided that my denominator is going to clean up to be h. All right, so f of 2 plus h. 4 plus 4h plus h squared minus f of 2, which is 4, all divided by h. Okay, guys, let's remind ourselves that we are still finding the slope between these 2 points, which is average rate of change. Average rate of change. Okay, so what can we do to clean this up? Okay, so the 4's combined to be 0. And then I notice that the 2 terms remaining both have a factor of h. So we could factor out an h. So what do we got? So factoring, you're dividing. 4h divided by h is 4. H squared divided by h is h. Because it divides to be 1, right? So guys, the average rate of change between those 2 points is 4 plus h. Now remember, average rate of change is slope between 2 points. I want you to understand why this formula for slope depends on h. Remember, we just moved over some arbitrary distance h. Would you agree that if I used a larger value of h, that the slope would be different? So we just found the slope between those 2 points. We're saying it's 4 plus this distance h. If I use a different value of h, like a point right here, would that slope be different? Yes. So the average rate of change depends on the value h. Over here, we worked on this same function. What was our value of h? 2, 3. So we got 7, right? So remember, the formula is 4 plus h. 4 plus 3 is 7. So the average rate of change is slope over an interval. So the formula for average rate of change depends on the width of that interval. Okay, but remember, what was our goal? Our goal was not to find the average rate of change. Our goal is to find instantaneous rate of change. So how can I do a better job of finding the value of the slope of that tangent line? What do you think? Elaborate a little bit? Use 0 for what? So, are you saying move this over? Well, it looks like if I extend this line like that, you don't understand anything? What part? Ask me a question. Maybe because I drew too much up here. Okay, so let's revisit what our goal was. All right, so guys, our goal is to find slope of that tangent. But we know 3 different formulas for slope. They all require 2 points. So we said, hey, let's just generate a second point. And I just arbitrarily chose one over here, and we found the slope between these 2 points. Now I can say, hey, the slope, this slope compared to this slope, is it similar? You're saying no? I mean, maybe, but how could I get a better approximation of this slope? What do you think? Just give it a guess. Like, just let's try something. Ask a different question.
So, when she asked, are those 2 slopes, they're similar to each other? Do you agree with that? Like, they're not the same, but we want that black line to have the same slope as the pink line, right? So what could we do? Okay, what can we do to at least get the black line closer to the slope of the pink line? Like, so slopes might still be different, but they'd get closer and closer to being the same. What could you do with what you have up there? Could you draw a different one?
So remember, what if this graph looked like this? What if I had chosen a point over here as my second point? Is that blue line a good approximation of the pink line? Okay, can we pull up that animation? Maybe we can use that animation. Maybe we need to see a better picture. What do you think? What are y'all thinking? Say something.
It's hard to not give it away in the question.
I thought you had it. Okay, so here's what we did. Our goal for this curve is to find the instantaneous rate of change, which we have related to the slope of a tangent line. Okay, but we said, hey, in order to use slope formula, I need a second point. So we moved over some distance h and created a second point. And once I have 2 points, I can calculate slope, right? I can calculate the slope between those 2 points. Now, compare the slope of that green line to the slope of that black line. Are they different? Yes, they're quite different, yes? In fact, we have the numbers, 0.45, 1.3484. So how can I take that? What can I do about that green line to have the slope be a better model for this tangent line? He's cheating. What? Okay, so think about it. What's going to happen as we slide this second point closer to my original point? So that's what I thought you were saying when you said zero, let it be 0. I was like, oh, what? Use more words. Okay, so watch, guys. The closer we get, because what was the goal? The slope of a tangent is slope at a single point. If I make those points as close to each other as possible, it's like I'm working with a single point. Yes? So, and when we let h go to 0, we can see, hey, the slope of the secant becomes the slope of that tangent. So, how do I let h approach 0? What's the L word? There you go. So guys, we are discovering the formula for a derivative, which is a limit of a difference quotient. Okay? Difference quotient. Think about that phrase. What does difference mean? Subtraction. What does quotient mean? Division. So we have a quotient of difference. It's a difference quotient. Is this right here a difference quotient? And anytime you're finding average rate of change, which you will be expected to do on the AP exam, you have to show a difference quotient. You have to show a clear division, and you have to show at least one difference. So make sure you show your work. All right, so this is our average rate of change, which depends on h, right? Because average rate of change is slope over an interval, so the slope depends on the width of that interval. To turn this into instantaneous rate of change, I want this h value to be 0. So we let h approach 0 by taking a limit. So to turn this into instantaneous rate of change, instantaneous rate of change, we take a limit as h approaches 0 of our average rate of change. 4 plus h. So guys, direct substitution would yield 4. So guys, over here, we have algebra. Average rate of change, slope between 2 points. Okay, you've been doing this for years. We put it through the limiting process. Okay, we take a limit as h goes to 0. We now have calculus, slope at a single point, instantaneous rate of change. Everybody okay with that? So the slope of this line, okay, the slope of the tangent line at x equals 2 on the graph of x squared is 4. Okay? So we got to make that connection. Average rate of change, slope between 2 points. Okay, slope of a secant. Instantaneous rate of change, slope at a point, slope of a tangent line. Okay? All right, so that was so much fun. Let's do it again. All right, so different function, but similar. Find the slope of the tangent, the graph of f of x equals x squared plus 1 at this point. Okay, and then we're going to use that slope to write the equation with tangent line. All right, so what's our formula for slope? Delta y over delta x. All right, so if you're a visual person, give yourself a sketch. What transformation is this for our parent function, x squared? Quadratic? Parabola shifted up 1 with the vertex at 0, 1. All right, so they told me that I want to find the slope at this point. They gave us the y-coordinate. What if they didn't give me the y-coordinate? How could I generate that y-coordinate? Just plug it in, right? But they gave it to us. We didn't have to work for it this time. All right, so we got this point. -1, 2. But our formula for slope requires a second point. So what are we doing? Move over some distance h, choose a second point. So guys, if we were at -1 on the x-axis and I move over h units, where am I at now? -1 plus h, the x value plus h. And then we would want to find the corresponding y-coordinate, f of -1 plus h. All right, what's our formula for slope? y2 minus y1, which, hey, they gave that to us, divided by x2 minus x1, which we know that that's going to clean up to be h because our delta x was h. All right, so this right here is what we have to work for. All right, so my function says f of anything is the anything squared plus 1. All right, what do we want that anything to be? What's the x-coordinate? There you go, -1 plus h, because we're trying to find the corresponding function value. -1 plus h. All right, so we're going to have to take -1 plus h times -1 plus h, and then don't forget this plus 1 as part of the function. So it says take that x-coordinate, square it, and then add 1. All right, so help me with this distribution. -1 times -1, 1. And then I have a negative h, and combined with another negative h, so minus 2h plus h squared. And then don't forget the plus 1. All right, so I can clean that up just a bit more. I can combine like terms, so 1 plus 1 is 2. So 2 minus 2h plus h squared. All right, so guys, remember, that was f of -1 plus h. So this right here is what we're substituting here. Okay, so 2 minus 2h plus h squared. Okay, so that's that first piece of the numerator. All right, minus 2. All divided by -1 plus h, take away -1. What do we get? H. All right, let's clean this up. What can we do? 2 take away 2. And the remaining two terms in this numerator both contain h, so we can factor. So h all right, so -2 plus h. So guys, what is this right here? -2 plus h. It's the slope of what? The secant, okay? That is the slope between those 2 points. And guys, look at this. How good does that look? That's awful, okay? So this is your average rate of change. This is your slope of a secant, okay? So this is slope of secant or average rate of change. Okay, or your algebra 1 slope. How do I turn that into instantaneous rate of change? How do we turn that into slope of a tangent? Limit as that delta x, which we call h, approaches 0. We want to slide that first point as close as or that second point as close as possible to the first point. We do that by taking a limit. So our slope of the tangent. Okay, at x equals -1 will be the limit as x approaches, sorry, not x, sorry, as h approaches 0 of -2 plus h. And I can evaluate this limit with a direct substitution. So what is the slope of that tangent? -2. Now guys, we drew this. Does it make sense that that slope be negative? Okay, because it's on that decreasing portion of our quadratic function. All right, so is that it? Did we find the slope of the tangent at this point? Check. But what else do we need to do? Write the equation of a tangent line. What do you need to write the equation of any line? A point. What else? So a y-intercept is a point, okay? But do I have to have the y-intercept every single time to write the equation of a line? Okay, it doesn't have to be the y-intercept. I could use the y-intercept. She said slope. So I need a point, any point, and the slope. All right, what's the point that we know? -1, 2. And what's the slope at that point? -2. We just worked hard for that. All right, point slope form. Y minus y sub 1 equals m times the quantity x minus x sub 1. And guys, that's just your slope formula rewritten. Okay? There's your slope, delta y, delta x. If I divide, slope equals delta y over delta x. Okay, so that's just that slope formula rewritten. So I can make substitutions here. So we've got x1, y1, and here's our slope. So y minus 2 equals the slope, -2, times the quantity, x minus a -1. So you're going to be writing equations of tangent lines a lot, and there is a purpose for why we're doing this, which you'll discover in Unit 4. Okay? Ultimately, we're going to be solving for y. Okay? We're going to be using this tangent line to approximate something. So another way you can write this is I can add the 2 to the other side. So -2 times the quantity x plus 1 plus 2. Either one of these is appropriate. Okay, if this is your preference, if this is how you've already learned to write point slope form, continue doing it this way. Now, on a multiple choice question, where it says write the equation of a tangent line, you write it like this. Okay, that's what you're comfortable with. Then you look at your answer choices. And then you manipulate based on your answer choices. Okay, so sometimes you'll have to move this over. Look at your answer choices. If none of your answer choices have parentheses, then you distribute and combine like terms. Okay, everybody good? Is everybody familiar with this? Okay, perfect. All right, guys, we've just discovered the definition of a derivative. Okay, definition of a derivative. What time is this class over? Oh, nice. Okay, so, guys, this is it. Your limit definition of a derivative. So, one of the notations for derivative, we say f prime of x. See the little prime? F prime of x. It is a limit of a difference quotient. Without that limit statement, it is not calculus. Okay? Without the limit, it is slope of a secant, average rate of change. Limit statement, now we have slope of a tangent, instantaneous rate of change. So guys, derivative. You need to understand what a derivative is contextually, so in context, and what it is graphically. So what is a derivative contextually? Instantaneous rate of change. What is a derivative graphically? Slope at a point, slope of a tangent line. Okay? All right, so here's our limit definition. Later on, you'll look at some situations when a derivative might not exist. So the process of finding the derivative is called differentiation. So here's that word differentiable. Okay, it's differentiable. A function's differentiable at x if its derivative exists at x. Some functions are differentiable over an interval. Okay, if it's differentiable if the derivative exists at every single point. All right, so let's do it again. Okay, so here we go. And like tomorrow, no, later on this week, what's today? Oh, okay, maybe early next week, you'll be able to look at this function and just spit out the derivative. Okay, until then, it's going to be a little bit painful. We got to do a lot of algebra to get the derivative. And then you'll learn a whole bunch of shortcuts to be able to just look at a function and find the derivative. All right, but until then, we got some work to do. All right, so I want to, for this function, I want to find the derivative at 3 different values, okay, 3 different x coordinates. So I'm going to find the derivative, okay, using our limit definition as a function of x, so that then I can just make substitutions. All right, so let's copy down that limit definition. So our derivative, okay, so this notation, f prime of x, notation for the derivative, is the limit as h approaches 0, f of x plus h minus f of x all divided by h. All right, so f of x is right here. So when we start making substitutions, we're going to substitute those 3 terms in place of f of x. But first, we need to find f of x plus h. So our function, the function rule says f of anything is the anything squared minus 3 times the anything plus 1. What are we going to use as our input? X plus h. All right, now we gotta clean this up. All right. All right, so since we've done this before, what's x plus h quantity squared? Everybody okay there? Okay, there's no shame in having to come off to the side and actually distribute, okay? It's worth the time to do that to not make a mistake. All right, so then here, I'm just going to distribute the negative 3. So negative 3x minus 3h, and then don't forget the plus 1. I'm writing really big. I'm going to run out of room. Okay, so now, for f of x plus h, we have to substitute all 6 terms. Okay? Why are you looking at me like you're angry? Okay. All right, so let's do this. I'm going to use this space down here, but I'm still working that same problem. All right, so we figured out we got to take the limit as h approaches 0. I have to write small. All right, f of x plus h. I'm copying down all 6 terms. X squared plus 2xh plus h squared minus 3x minus 3h plus 1. Whew. Now remember, that's just this first piece. From that, we need to subtract f of x. Now guys, how many terms is f of x? 3. How do I ensure that I subtract all 3 terms? There you go. Group it, group it, group it, group it. Don't forget to group after your subtraction. So minus all 3 terms of f of x, which was x squared minus 3x plus 1. Oops. And all that is divided by h. All right, we got to start cleaning this up. So here I have an x squared, and over here we're taking away x squared. So x squared, take away x squared. Here we have a negative 3x. We're taking away negative 3x. So 3x take away, sorry, negative 3x take away negative 3x combines to be 0. And then here I have 1 take away 1. So you see how that whole function subtracts out? So what do you notice about the 3 terms left in your numerator? All right, so I'm so sorry that I'm writing all over the place. So we can factor out an h. So remember, when you're factoring, dividing 2xh divided by h, 2x. H squared divided by h is h, and negative 3h divided by h is negative 3. Like, just quickly eyeball it and make sure if you were to distribute, you get back to where we started, or back to that previous step. All right, so now what can we do? Okay, h divided by h, that divides to be 1. And now when I take my limit by a direct substitution, okay, we replace h with 0. What is our derivative? There you go, 2x minus 3. All right, what is a derivative graphically? Slope at a point, right? Slope at a single point. That's right. Instantaneous rate of change. So guys, why does this depend on x? So what does this graph look like? Because this is a quadratic function, right? I don't know where it is on the coordinate plane, but I can draw a sketch of a quadratic function. Would you agree? This is my tangent line. This is my tangent line. Would you agree that the slope at every point on this curve is different? So the slope depends on the x-coordinate. Okay? So we ended up with a formula for slope that depends on x, because the slope at every point on that graph is different. All right, so we want to find the slope at these 3 x-coordinates. Now remember, our formula for finding slope, 2x minus 3. You guys, next week you'll be able to look at that and say, oh, I know the derivative, it's 2x minus 3. Okay? All right, so let's do f prime of negative 1. I'm so sorry that I'm all over the place. So here's our formula. This is like our recipe for finding slope at a point. This formula, this recipe, only depends on the x-coordinate. So if they give me an x-coordinate, I can find the slope at that point. So 2 times negative 1 minus 3. So what would be the slope at, there you go, negative 5. All right, my next x-coordinate is at 0. Is that right? So 2 times 0 minus 3. Negative 3. What's our third point? Third x-coordinate? 2. All right, f of 2. 2 times 2 minus 3. 1. So I have 2 slopes that are negative, and then over here, a slope that's positive. All right, so there's a lot of algebra, yes? So I want you to understand, we used that formula that was given. We did algebra, algebra, more algebra, more algebra, and then we did one little step of calculus by taking a limit. So, sorry, I didn't know the bell was withering. I wasn't watching time. Oh, yeah.